Yes, so in the immediate previous section, we concluded by looking at the problems with homojunction lasers, no carrier confinement and no optical confinement. So if you are not sure of what these terms mean, I would encourage you to pause this video, go and look at the immediate previous video and come back. So yeah, assuming you are familiar with carrier confinement and optical confinement, what is the solution to the problems we discussed there? Something called a heterojunction. Hetero means again different or multiple things which are not the same, of course, different rather than multiple. And junction again is the p-n junction. So what we have here is two p regions and two n regions corresponding to different materials. So the inner light blue p and n are the p and n regions of the gallium arsenide semiconductor. The outer ones are the p and n regions of the aluminium gallium arsenide semiconductor respectively. So the p and p are put together, n and n are put together, but the inside pn belong to one semiconductor and the outside pn belong to another semiconductor. Now you cannot just put any semiconductor with any other semiconductor here. In choosing the materials, these two properties have to be kept in mind. The band gap of the outer element or the outer material should be greater than the band gap of the inner material. Refractive index of the outer material should be less than the refractive index of the inner material. So I repeat, a heterojunction is a laser, an active medium for a laser, where you take two different semiconductors, you put the p types together and the n types together and sandwich all of them. And in choosing or in arranging your materials, you need to make sure that the outer material has a greater band gap and a lower refractive index than the inner material. So how and why does this help? So we will look at these graphs quickly and then we'll understand how the heterojunction works. So firstly, this is your normal homojunction. This is single heterojunction and this is double heterojunction. So what are single and double heterojunction? In single heterojunction, you just add one layer extra, meaning inside I have p and n, outside I will either add a p alone or an n alone. So here, if I just add the p of AlGaAs and I did not add the n, or if I added only the n and not the p, that would be a single heterojunction. If I am adding both the p and n layers of the second material, it becomes a double heterojunction. That is that. So this is the diagram we already saw when we were just looking at an intro to semiconductor lasers, normal homojunction. This is in single heterojunction where we only add the n layer extra. So your holes are as usual, they are the p region that ends here. Actually it ends here and this is the junction region, and your n region, it is a little extra, it extends up to here because you are adding one extra n region. And double heterojunction, you are adding both p and n. So this is just the basic energy level diagram. You have valence band, conduction band. In the normal homojunction, it is a smooth energy gap. Here, because you have two p regions and two n regions, or at least one n, whatever in this case, because you have multiple regions of different semiconductors, it is not a smooth transition between energy levels. You have this kind of a stepwise increase or decrease. This is the band structure. Next is carrier density. So homojunction, holes and electrons are more or less same, and this area is where the recombination happens. Single heterojunction, because I am adding an extra n layer, electron concentration rises. Holes is just what it was. Double heterojunction, both the concentration or the carrier density rather increases, in the sense that more charge carriers in less space. Here they were spread out over a larger space. Here most of them are spread out within a smaller space. The number is high. This is what we mean by carrier confinement. You have a large number of charge carriers confined within a smaller space. So how this happens, I will explain. But yeah, you understand that you understand the diagrams. Refractive index, again homojunction, it is just one thing. Heterojunction, here in the n side I have an outer material and it has a lower Ri, as was the condition. Double heterojunction, both the p and n sides I have the second layer which has a lower Ri compared to the first layer. Optical field, as in power of the output, this is the normal power range or power versus wavelength graph for a homojunction. For a heterojunction, you can see that the graph becomes narrower on the side where we are including a second layer, and double heterojunction, both layers, the power becomes greater and the wavelength spread is decreasing. So what does that tell us? As you increase or as you start adding that extra layer, the power increases and the monochromaticity also increases. The wavelength spread decreases, monochromaticity increases. So it looks, at least from these graphs, like this double heterojunction is helping us create better laser light, right? Better in the sense, we saw from this graph that there is carrier confinement. Here we are seeing that it's giving higher intensity, because greater power means greater intensity, and more monochromaticity, which are some of the prerequisite properties of a laser. So it seems like heterojunctions, particularly double heterojunctions, are a good idea. So why or how exactly, we'll look at that now. So this is an example of a double heterojunction, but this diagram is too complicated. So from an exam perspective, this diagram will suffice for double heterojunction. You don't need to go into that. These are the things we need to remember. So firstly, just a couple of points we will brush up again before we study double heterojunction. The outer material should have greater band gap and lower refractive index than the inner material. Now, a larger band gap and lower refractive index, it guides photons by TIR, photon confinement. So let's say you have an outer material and an inner material. So the outer one has lower Ri, the inner one has greater Ri. It sort of becomes like a core cladding equation, right? So the core has greater Ri, cladding has lower Ri, core lies inside, cladding lies outside. What happens? TIR happens in your optical fibers, and the light wave or the signal stays inside the tube. Similarly, your inner material has more Ri than your outer material, so the photons do not get refracted and go out. The outer material guides them back inside, so they lie within the system. That is photon confinement or optical confinement. That is why when you have this extra layer, the power increases, because more photons are going to remain inside the system. The loss of photons is minimized. Secondly, a larger band gap material prevents the flow of carriers away from the junction. So carrier confinement. Now, how to explain that is, you look at this diagram and this one, for example. So this is your normal homojunction laser. So let's say this part refers to the junction region. You can probably see some 5 to 6 holes and 5 to 6 electrons. But here, because you are adding one additional P on this side and one additional N on this side, because of this step, the junction region widens, meaning more electrons and holes are in the junction region first of all. So more recombination is going to happen firstly. And secondly, it will not allow these electrons to flow away. So because there is this wall here, what is this wall? Not a physical wall, obviously. It's like an energy barrier. So here the energy levels transition was very smooth. So the energy difference between this part and this part would be very less. But here, because you have one more material and that has a greater band gap, so the energy difference between the junction region and the next P, the outer P type, for instance, would be very high. So these holes would not be able to cross that energy barrier and leak out. Similarly, these electrons would not be able to cross that energy barrier and leak out of the material. So what remains in the junction region remains there. So the carriers are confined. That is this. So larger band gap helps in carrier confinement, because the energy gap which your charge carrier will have to jump across becomes higher because of that extra layer. So it cannot jump across, it stays there. Leakage of charge carriers is avoided, so more recombination, better laser light. So yeah, to quickly summarize, this is a double heterojunction. The outer layer has lower Ri than the inner layer, so that TIR will happen and your photons do not leak. It has a greater band gap, so that the charge carriers cannot leak out and escape. and hence the carrier concentration or carrier confinement is better, optical confinement is better, hence your laser light, you get better laser light, for want of a better. So yes, that's that. Carrier confinement, optical confinement. This is just the evolution of lasers across different levels, different generations. Homojunction and heterojunctions are the ones we mainly deal with in this chapter. And I think that brings us to the end of lasers.